if I swing my keys around in a vertical circle like this, you can see right now that clearly these keys are moving fast enough to stay in the vertical circle. But you know that if I slow them down, at some point, the keys will fall out of the circle. Right now, going a little bit too slow, the keys aren't going in a circle anymore, right? You need the speed of the keys to be a certain value or greater in order for them to stay in the circle. What is that speed? How fast do they need to be going? Well, let me ask you this first. If they're going to fall out of the circle because they're going too slow, where's that going to happen? Bottom, top, somewhere in between? Yeah, if they're going to fall out of the circle, it's going to happen at the top. So let's start drawing a Freebody diagram for that, and then let's deal with what we have to do with it. At the top of the circle, we have a normal force acting down, and we have a force of gravity acting down. And we're going to say, as we always do, F net is equal to the sum of the forces, Fn plus Fg. We're going to say F net is equal to mv squared over r, and we're going to say Fn plus, we'll make Fg m times g, right? Watch the keys again as I swing them around. Okay, right now they're going fast enough, more than fast enough in fact, they stay in the circle. If I slow them down, at some point they drop out of the circle. Just before they drop out of the circle, I want you to watch the string. Look at the string and look at how hard the string needs to pull when I'm going just barely fast enough to go in the circle. What's the tension in this string right now? What is it? Not very tenuous, he says. In fact, at the minimum possible speed, the tension in the string is actually 0. When you're at the minimum possible speed, the only force you need to cause the centripetal force is gravity. Gravity acts down, and when you're at the top of the circle and going at the minimum speed, that's enough to keep it in a circle. If you go faster, you need the normal force to help gravity keep it going in a circle. But at the minimum speed, you only need gravity to cause it to go in a circle. Okay, remember that. That might be a good thing for me to ask you in a multiple choice question at some point down the road. Okay, what provides the centripetal force when you're going at the minimum speed? What provides the centripetal force? It's only gravity. The normal force doesn't have to push at all. Gravity can do all the work for you. So if that's the situation where we're going minimum speed, the normal force doesn't have to act at all, let's cross that off. Now my equation becomes mv squared over r is equal to m times g. Notice the mass cancels. That's good news. If you're on a roller coaster, you don't want to worry about who you're sitting beside. Okay, one person sitting beside a 90-pound kid, other person sitting beside a 300-pound guy. You don't want to worry about sitting beside the 300-pound guy, going around the loop and then falling out of the loop because the person's really, really heavy. It doesn't matter. The masses cancel. It doesn't matter whether you're beside the 90-pound person or the 300-pound person, the masses cancel. Listen, I want to find the minimum speed, how fast it has to be moving in order to stay in the loop. Let's set Fn equal to 0 because at the minimum speed, the track, the string, whatever, doesn't have to push at all. It becomes v squared over r is equal to g. Now, I would just sub my numbers in and solve for v. That's it. That's all there is to it. When you want to find minimum speed, all you got to do is set it up at the top of the circle and make Fn, the normal force, equal to 0. Now, similarly, you could be asked a question, in fact, you will be asked a question on your worksheet that asks you not for minimum speed, but maximum radius. Same deal. If I make my speed too small, the keys fall out of the circle. If I make my radius too big, the keys fall out of the circle. In both of those cases, all you want to do is set Fn equal to 0 and then solve for v. Let's do an example. So example number 4, it says, what's the minimum speed of a roller coaster car moving in a vertical loop of radius 10 meters? Now remember, I'm looking for minimum speed here. I'd do this the same way if I was solving for maximum radius. Analyze the top of the circle where Fn is acting downwards and Fg is acting downwards as well. We're going to say F net is equal to the sum of the forces, Fn plus Fg. But when we're solving for minimum speed, the normal force will be equal to 0. So that makes mv squared over r equal to m times g. M's cancel, which, as we said, is good news. You don't want to be on a roller coaster worrying about how heavy the person next to you is. Let's sub in some numbers here. Solving for v, r is 10 meters. G is 9.81. I'm going to make both of these terms negative because gravity is acting down. And since I started plugging in numbers for the centripetal force, I have to pay attention to the fact that it's acting down as well. But the good news is, even if you forget those negatives, they end up canceling in this question, right? If I cancel out those v's and take the 10 out by multiplying, then v squared is equal to 98.1 newtons. And if I square root v, I end up getting a speed of 9.9 meters per second. So if this roller coaster car is going at 9.7 meters per second, it doesn't stay on the track. It falls out of the track. It doesn't go in a circle anymore. If it's going at 10.2 meters per second, it goes in the circle just fine. You might get a little nervous because of how slow you're going, but it's safe as long as you're going more than 9.9 meters per second. Now, just a quick little question before I let you work on a couple questions on your worksheet. If you're going around this loop like this, in a vertical circle like this, and you're going at 9.5 meters per second, you're not going to get to the top and then fall down. You only fall straight down if you're moving at the minimum speed. Rather, what happens here, we get to the top of the circle, if we're going, say, 9.5, 9.7 meters per second, it's going to leave the track like this. It's not going to fall straight down. It's going to keep moving, but it's also going to fall. What would the shape of this path be right here? It's a parabola. Now it's projectile motion, right? When it's going around the circle, it's circular motion, but then when it leaves the track, it becomes projectile motion because it goes in a parabola. Don't worry, I'm not going to give you a problem where you have to deal with the circle and then the parabola within the circle. Although that would be a great question. I won't do that to you. All right, here's what I'd like you to do. You did courses 1 and 2 on worksheet number 21 already. I would like you to do the last 2 questions on worksheet number 21.
He starts to wind up in the elevator with the ball.
Let's look at number 3 here now. It says a kid on a bike, total mass 110 kilograms, decides to go around a vertical loop of radius 8 meters. I'm not sure that this is necessarily the wisest decision of this kid, but if this kid can go fast enough, he or she will go around the loop and be safe. You've got to make sure that you're going fast enough. How fast does that need to be? Well, we analyze the top of the circle. When we're analyzing the top of the circle, we make the normal force equal to 0. So F net is equal to Fn plus Fg, but we cross off Fn. So it becomes mv squared is equal to m times g, but then we can cancel out the mass. As we said before, it doesn't matter how heavy the person is, the minimum speed will still be the same because mass cancels. V squared over r is equal to 9.81. Both of them are negative, but the negatives cancel out. The 8 goes up by multiplying. 8 times 9.81 is 78, and then we square root that, it becomes 8.86. You're going at 8 meters per second, you fall out of the loop. Okay, that's bad news. You're going at 9 meters per second, although it might be a little scary to be biking upside down like this. Okay, in the end, you're still going to stay in the loop and you're going to be safe. Good? Number 4, similar question, except this time you're looking for the max radius of the turn. This is like finding the minimum speed. You cannot be below a certain speed in order to stay in the loop. You can't be above a certain radius of a turn to stay in the loop. In both cases, we're going to make Fn equal to 0. Analyze the top of the circle, make Fn equal to 0. mv squared over r is equal to m times g. M's cancel again. V squared over r is equal to g. But this time we're actually solving for r rather than v. So r becomes v squared over g. 1.5, because we're in meters per second, divided by 9.81, gives me 0.229 meters. Now be careful here. You don't want to be above 0.229 meters for the radius here. You want to be below it. You want to be above a certain speed. You want to be below that radius. Yeah, this is the maximum radius, so that's a good question. If you're at that radius, it's okay. Okay, just like that minimum speed of 8.86, if you're at that minimum speed, you're okay. You just don't want to be below.